I'm presenting this paper, eye tracking for performance evaluation and workload estimation in space telerobotic training. This is my reading assignment. Presentation is given below, and the link to this video will be updated as the recording ends. So now let's take firstly a quick look at this paper. Its main contributions, I think, is that it tries to estimate the presence of external factors like control delay and time pressure instead of a simple binary estimation of high or low mental workload. It also tries to put these factors simultaneously in a single line of study, unlike some previous work where they are isolated into different analysis. The authors believe that their variable remapping of action and time ratio is also a contribution, but I think it offers very limited improvement, as we'll see later. That is why I'm not putting it here. The strength of this paper includes great data presentation, preparation. I think they're doing a lot to reduce noise to the results. The authors also try to approach this data set in various angles. The results are mixed. Some are more successful than the others, but overall, this holistic perspective is one of their biggest strengths. The main limitation of this paper is that only 10 volunteers are recruited. As the authors themselves say, they can definitely benefit from having a larger sample size. Also, their future research plan of real-time factor estimation is a very ambitious goal, but approaching it from purely eye tracking is limited. The authors themselves realize that with more types of sensors, maybe a better correlation can be found. The authors themselves think that they can randomize delay and time pressure in a larger range. To that, I fully agree. To illustrate the motives of their method, the authors discuss relevant work in the field and their shortcomings. There are three groupings in total. The first group of work examines the effects of input of feedback latency on the human operators, as well as the effects of time pressure on them. Multiple studies across disciplines came to more or less an agreement here. Increased latency damages operators' focus and sometimes their emotional states as well. A moderate amount of time pressure can increase efficiency, but further increased time pressure will become more negatively impactful. The authors then point out that none of these factors have been studied simultaneously and their combined effects examined. The second group of work develops methods to estimate workload based on physiology data. Various signal analysis techniques have been performed on pupil dilation. The phenomenon of gazing an area for a long time, known as eye fixation, and that of looking around different areas rapidly, known as eye saccade, have also been examined. There are also studies correlating blink frequency or duration with workload. Other workload estimation studies have heavily utilized EEG or other physiological data. The authors criticize that none has been done to study estimation of workload induced by external factors like latency and time pressure. The final group of work finds different gaze patterns are an indicator of expertise, and those more skilled have relatively less mental workload. It is unclear, though, the purpose of authors mentioning this line of work, other than showing a breadth of literature review. If we look further into the paper, it is actually closely related to the final section of the results section, but I think the author simply forgets to mention that here. So the experiment is set up with three main components, the O-cubed simulator, the external factors, and the eye tracking device. The picture here shows the simulator and the task setup. A 7 degree of freedom Canadarm2 is controlled in simulation with a PlayStation controller. Operators need to strategically activate various cameras in the middle figure here and change their angle within range. They need to approach and grasp a research module. They want to bring it back with a robotic arm without collision with static debris, and they want to safely dock the module into the port. Operators receive a score of this operation. The score increases when the grasping position and orientation is more precise, when fewer collisions are made, and when the operation takes less time. The second component of this setup, which are external factors, are introduced into this operation. A control delay of either 0, 0.5, or 1 second are introduced randomly in each trial. A time limit of 4 minutes is also added randomly. This is the final part of the setup, which is the eye tracking device. the operators need to wear this camera set. That the backward cameras capture images of each eyes. The frontal camera looks at the screen in front of them. Pupil center and diameter information are combined with the frontal image to reconstruct gaze location on the screen. The authors note that calibration is done every 2 trials, which is quite frequent and should ensure accuracy. My question on it is that this device looks very uncomfortable. There added weight on your head, added pressure with the circlet or the frame of the headset, and 2 big chunk of eye cameras, and their structure supports blocking your sight. I'm wondering if this setup itself impacts mental workload, and if something less intervening can be devised. There are a few things noteworthy in their data collection. The first is that they distinguish the concept of trial and segment data, where segment data is a subset of the entire data during the whole trial. In this case, segment duration can be 2, 5, 10, or 20 seconds, and they do not overlap. This is preparing for the future research of real-time workload identification. The second is their normalization. The authors notice change of pupil diameter on the same operator between trials due to fatigue, so they record diameter changes as their dataset instead of the raw diameter value as a signal for the dilation. They also perform z-score normalization for each operator to address differences between individual operators. More importantly, I guess I should say most importantly, the authors list the features they use to track the eye. A number of metrics are used for both eye fixation and saccade tracking. Oddly, though, the authors claim they're able to track smooth pursuit of gaze, but they didn't provide a reason why they do not. Various metrics are used to properly describe blinking. A wavelet analysis was used on the pupil response that reduces influences from lighting. The authors also are tracking ratio of time the operators spend gazing on each camera and outside the user interface. Finally, 10 volunteers are recruited as operators for the task. Overall, I'm very impressed with these treatments. I think they're quite thorough as considering all possible factors outside of scope of this study, and these are valid measures to reduce their influence on results. So what do the authors plan to do with this setup and data? They're trying to verify the literature observations of the effects of individual external factors on the eye tracking data. They are trying to use the eye tracking data to classify what kinds of external factors are present. They're also trying to see how the performance of certain tasks are improved by certain cameras or are highly related to certain features. The authors first discuss effects from single factors using only trial data, and what really matters are the arrows in the blue boxes. They indicate increase or decrease of that metric with the external factors comparing to without the external factor. It's seen that with added pressure, the operators become more focused and gaze more, they blink less, and their mental workload increases based on pupil features. With added latency, the operators gaze center move around more. The authors specifically note that many operators get used to the latency and adapt to it, which is likely cause of the relative little impact of control delay. Next, the authors plot 4 key metrics across different groups. The metrics are mean fixation duration, IPA, saccade frequency, and mean saccade speed. The groups are conditions when no time pressure or latency is present, only one is present, and when both are present. The results agree with the previous chart. The more external factors, the less gaze duration there is, the more frequent saccade occur. An eccentric increase of IPA and thus mental workload is observed when time pressure is present, which is aligning with common sense. Saccade frequency seems to be the least impacted. In workload identification, the authors use both trial and segment data to classify presence of each factor and classify the whole situation into one of the 4 aforementioned groups. In each trial, data from one operator is the test set, and those from the other 9 are training sets. A support vector machine with radio basis functional kernel is the classifier. In these tests, a rather uniform pattern occurs. This pattern consists of several observations. First, ANOVA features from trial data consistently outperforms segment data in terms of classification accuracy. since its long horizon reduces short-term volatility. Secondly, for the same reason, a 20-second segment time outperforms a 5-second one in the most cases. Thirdly, training accuracy, denoted by val-ac in table 4, is better for shorter segments since training set is larger. Finally, the accuracy by themselves are not impressive. Most are around 30 to 50%, with trial data ANOVA being over 70%. That's the max. I think this is hardly useful in real life. Apparently, there more could be done and should be done if this idea is to be realized. As the authors point out themselves, identifying influential factors from an intrinsically hard model process is very challenging. So they devised a way to remap the independent variables by defining the action ratio, which is the time spent when operator is issuing control divided by the segment duration. They also define a variable called time ratio, which is a normalized value showing when in the trial this segment data is taken from. They're able to show limited improvements when using these remap variables in classifications, especially when training the classifier with small action duration and small time duration data. In other words, external factor prediction is slightly better when the operators are not spending extra energy controlling the arm and in the beginning of each trial. As you can see in this plot, the rightmost green bar is performing better almost with all metrics in all 3 classification tasks. I can't help but to offer my critique here, however. The improvement they show is really marginal. As you can see on the plot, it's an increase of at most about 12%. It can be a solid step going forward, but still far from real-life deployment. Meanwhile, limiting classifications to periods of little control input and in the beginning of the trial is against the motivation of real-time external factor identification. If the time to do classification is so limited, there's no point of doing it in real time and to do it a continual tracking. However, I do find the results in the final section of the results quite interesting and very informative. When correlating eye tracking data features like mean pupil diameter, mean fixation duration, and IPA with the final performance score, a clear trend can be observed, and it agrees with the relevant studies the authors themselves cite. In the leftmost plot, the larger the pupil diameter, the less focused the operators are, and the lower they score. In the middle, the longer fixation duration is, the more focused they are, and the higher they score. In the right, moderate mental workload increases scores, but too much mental workload damages them. The authors then go on and analyze how the usage of each camera contributes to the score. Looking at the left column, it's apparent that camera 2 is very seldomly used in both grasping and docking tasks, and this leads the authors to identify its problem of poor lighting. I think this is really helpful in optimizing the camera design or even the robot design as a whole. Showing which camera is underutilized by the operators is exactly the kind of user feedback any design optimization relies on. On the right column here, they then find an interesting trend that focusing too much on certain cameras like number 1 and 4 can damage the score. This is again a valuable user feedback that can be used to train future operations to learn to pay special attention to certain cameras, since they're perhaps better positioned for this kind of task. So what are the conclusions here? If we look at the effects of individual factor, it's apparent that time pressure causes high workload, and control delay can be adapted to by the operators. In terms of factor identification, we learn that remapped action and time ratio offers improvement, but they're really not a good reason for them to be applied. And of course, we know that more sensors may be helpful to help classify in a higher accuracy. In terms of task performance, of course, we see that the more focused the operators are, the higher they score. We're also observing that moderate time pressure lead to highest performance. Overall, I think this is a great paper. It has good data preparation. It has holistic perspective of analysis. It has informative results. I think this is a good work to base your own research on. So what can you do on top of their existing work? You can try to address any of the limitations we've mentioned in the overview. You can try to increase the number of operators so it covers a larger sample size. You can try to increase the sensor for more accurate real-time factor estimation. You can also try to add more noises so that the randomization covers a larger range. Those are all things you can do. And that ends my presentation. Thank you for listening.